Hello, everybody. In this session, we will continue in the quantum machine learning with engineering Abdulrahman. If you have any questions during this session, please feel free to raise hand. Let's get started.
Okay, hello everyone. I hope my screen is shared and you can all see my screen. Okay, today is our last session for the track. We have understood the quantum machine learning workflow, the quantum kernels, and the fundamental model, which is quantum neural network, and how the models are being trained and used in quantum computing. Today, for our last session, we will have a small discussion about hybrid quantum machine learning using approaches that depends on classical machine learning and quantum machine learning in the same pipeline. So, for our big question, if quantum computing is so powerful, why are we not replacing classical machine learning? That's the first question anyone would ask if I told him about quantum machine learning. He will ask if it's so powerful, why we are not replacing the classical machine learning. So the answer for this question depends on many criteria. Our era right now, it's NESC era, noisy intermediate scale quantum. So limited number of qubits, we can't let's say if I have millions of features, I can't represent them using the current number of qubits. And of course, noise and decoherence. I can't use ansatz with many layers because of the noise. And error correction. In our era, there is no fault tolerant quantum computers. So we need to use multiple qubits to represent only one qubit. It's called logical qubits and physical qubits. So we can't uh, we don't have the freedom to use all the qubit with the same fidelity, and of course expensive measurements. As we have seen last session, we need millions of shots for only one data point in each epoch, so it's very expensive in terms of measurements. So these constraints prevent the execution of large, deep, fully quantum algorithms. So there is this term that's called pure quantum machine learning. This approach aim to build fully quantum models such as quantum support vector machines, quantum neural network. There's others that's called HHL based algorithms. It is used to solve a set of linear equations. It's out of scope of this track. Um, these kind of models are built to pure quantum machine learning. But of course, there are limitations. The data encoding, uh, most of papers use amplitude encoding. It's the most efficient. It uses only logarithmic scale of length of features, but it is very, very expensive because of the initialization and initializing the state vector for each data point. And extracting results require many measurements. We don't have access to the state vector directly, so we need to measure a lot, thousands of shots, so we can reconstruct the amplitude from these measurements or calculate the observables. No consistent deterministic quantum advantage in practice. All the quantum advantage right now for quantum machine learning is only theoretical advantage, but in practice, right now in our era, there is no proven quantum advantage. So we can just say we can use pure quantum machine learning models. So for our current era, instead of replacing classical machine learning, the focus shifted towards combining both approaches. So a hybrid models is quantum and components are integrated into single computational and learning pipeline. Let's say, for example, for all the models we have taught, they use pre-processing and post-processing, uh, which are classical um, processes. So the quantum itself can't get the raw data without the encoding, and the encoding cannot be done without the pre-processing, the mapping to actually inject the data into the encoding step. And for the measurements, we need to um, use classical computers, HPCs or GPUs or whatever, to calculate the observables from the measurements and then calculate the gradient, let's say with parameter shift rule, and then optimize the parameters and then inject it back to the model. This whole stage is done by classical computers. So right now, we can say all models don't fully function on quantum circuits or quantum computing. They are hybrid in some how. So what we're talking about here, hybrid models, uh, is the model itself, not the pre-processing or post-processing. I'm talking about the model itself is integrates both classical and quantum components. So in the lab on and notebooks, we'll see we'll get a better understanding on how it's done. Okay, so why hybrid models make sense? Classical systems excels at optimization, scalability, and data handling, and quantum systems offer high dimensional representations and complex transformations. Uh, this advantage in quantum system, which is high dimensional representations, actually a good fix for the curse of dimensionality for the classical systems. And data handling in classical system is a very good fix for the data encoding and post-processing for quantum systems. So if we integrate both of them into one pipeline, it could give us somewhat of an advantage. So uh, let's say we are working on a paper or a competition or a hackathon. So we want to work within hardware limits. Use shallow circuits instead of deep ones. So we initializing ansatz, start with one or two layer, and for the encoding, we can start with the Z feature map instead of the ZZ feature map, and operate on a small number of qubits. So this is if you are actually working on hardware. But if you are working in a simulation or using the state vector directly, you can experiment with higher number of layers, higher number of qubits. But in hardware, the for the limitations, for the noise and limited number of qubits, use shallow circuits and a small number of qubits. And for the measurements, if you have 3 to 4 qubits, you want to have more than 10,000 shots to actually get a better understanding of the state vectors. So you can reconstruct the state vector itself. I can also show you how it's reconstructed. Let's say the measurement. I have 2 qubits. This is 200, for example. This is 500. This is 100. And this is 200. So I ran the circuit for 1000 shots. And this is the counts and the measurements. So I calculate the probability for each one. This is 2 over 10, which is 0.2, and this is 0.5, 0.1, 0.2. And to reconstruct the state vector, we knew that the amplitude besides the state is actually the square root of the probability. So we take the square root 0.2 and we do the same until we reconstruct the state vector. So this is how it is reconstructed without actually getting it from the simulator or using state vector directly. So within hardware limits or using hardware, we run the circuit for many shots so we can reconstruct the state vector, and then we can calculate the observables and anything we want. So it is very expensive to, let's say, we want a good approximation for a higher number of qubits to get to reconstruct the state vector. So the overhead actually kills the quantum advantage. So there is other ways, many work in the state of art on using something called repeated measurements. Uh, it's part of the, if you know statistics. So if you want, you can read about it. So this is some tips on working with hardware. So how training is done in these hybrid models. Gradient based optimization for the classical part of the model. It's gradient based like Adam optimizer, so it's a normal. And for the quantum part, we use the same optimizer but using parameter shift rule, and it's integrated with classical machine learning frameworks like PyTorch or TensorFlow and efficient parameter updates. So there are three main ideas on how it's done: quantum feature maps, using the quantum models and the quantum circuits, and input the data to get a new or a more complex representation of the data. So let's say I have three qubits and three features, for example, and then angle encoding, the ansatz, and the measurement. For the measurement, I will get the observable for each qubit. And these observables, each one of them are bounded from 1 to -1, from -1 to 1. So this is my new features. So I'm using quantum circuit and train them to get a better representation of the features. So it can be easier to separate, for example. Um, so these features are then fed into the classical neural network or classical model, whatever. So this is one way of thinking about using hybrid pipelines. There is another way, which is variational quantum layers, is to use quantum circuit as a layer with the neural network. So let's say I have two layers, which are classical neural network, normal classical, and then one layer, quantum layer, then one classical layer again. So the input, let's say I have 1,000 feature data. It got it reduced to 256, and then let's add another layer here to 16. Then these 16 features are the input for this 16 feature can be reduced to 4 feature using amplitude encoding. So it can be 4 qubits. Then the output are then fed to an output layer to then let's say we can apply sigmoid or softmax at the end to the classification problem. So it's to integrate a quantum layer inside the neural network workflow. And there is another way which is called quantum reservoir computing. It's a new topic, an advanced topic. The quantum system itself is fixed and not trained. So the quantum circuit doesn't have the rotation gates that has the angles that are being updated. It's a fixed circuit which represents the data in a wave equations format. It can, and the measurement from it produce the features which will be then fed to the quantum for the classical layers. So this is our three main or three fundamentals approaches on how it's done. There are many other ways. For the training, for the classical part, a standard backpropagation for a neural network, and for the quantum component, gradients are calculated using parameter shift rule. Okay. Key advantages. Quantum systems can represent complex and high dimensional states. Quantum circuit naturally embeds data into rich feature spaces, and quantum component can be inserted at different stages of the model. Okay, so the current state of the art achievements. Most papers work on a small scale hybrid model implemented. So they start, for example, with a two layers classical data, classical models. Then they add another quantum layer, and they do the same input data, the same random seed, and they see how much it takes, the metrics has have been improved or not. So this is what they are working on, and a proof of concepts experiments. Okay. Limitations: no clear, consistent quantum advantage in the current time. Limited scalability. It can't be done on a large scale. We can't use, as we have said, like more than 10 qubits maximum. So this is a limitation, and sensitivity to noise. Okay. And the challenges: barren plateaus, as we have said in the last session. Barren plateaus makes the gradients nearly zero, so it's vanishing gradient. So the parameters and weights are not updated. Measurement overhead, we need to measurement and in millions of shots. Data encoding bottleneck, if you want a more efficient data encoding method, you will have to face the increasing in depth and noise, and of course hardware limitations. So this is why they are shifting towards hybrid quantum models, and our limitations in the current era and the state of art they are working on. So this is our first notebook of the day, which implements a hybrid quantum neural network with MNIST dataset as as the last session. The new thing here, we will integrate another framework, another classical machine learning framework, which is Torch. It implements nicely with Penelane. These imports are the same from last session. We only these both are new, Torch and Torch neural network. The configurations for the two classes from the data as the last session. Number of features here. Our notebook implements the classical neural network first, then the last layer is a quantum layer. So it's like that. So let's say this is classical layers, then one quantum layer here, then lastly an output layer, which is also classical. Okay. So number of features, that will be the input for the first classical layer. Number of qubits, number of layers for the quantum neural network, number of epochs, batch size, two different learning rates. Learning rate for classical, here it's a bit small, and for the quantum it's a bit large. Um, Here the classical is the first model, so it needs to heat up using a small learning rate, and for the quantum, the the features are already, the classical model already have done the heavy part, so we can use a higher learning rate for the quantum model. And the same as the last session, number of samples for training and testing, and of course for to reproduce the same data we need the same random seed. Okay, the same thing here, loading mnest and masking it to get the 2 digits, visualizing 10 random labels and data, 6 and 3, and of course encoding the labels to be only 0 and 1. It's a binary classification problem. Normalize and then reduce using BCA. Here we are not reducing to the number of qubits like last session. We are reducing to the number of features for the first classical layer. It's 180 and 128, and explained variance is very high here, and we are splitting the data. So this is all repetitive. This is the new part. How the quantum circuit will be integrated with torch and the classical neural network. Last session we have talked about the device, the same device here, the folded qubit, the same number of qubits, the same exact variational layer. But here the wrapper itself is different. Interface here is torch, not autograd, it's torch. So when integrating with the torch framework, it can integrate nicely for the optimization and calculations of gradients. So here, angle embedding and applying variation layer for the number of layers. Here, this is new. For the output, I will get the expectation value for all for each qubit. So not only the first qubit, for each qubit. So if I have 4 qubits, the output will be a vector of 4 observables for each qubit. And then this vector will be the input for last layer, which will be into one node and apply sigmoid function so we can apply the classification problem. So here it must be getting the expectation value for each and all the qubits. Okay, visualizing the circuit, it's the same circuit from last session. The only difference, you see that the measurements are applied on all qubits, not only the first qubit. 16 trainable parameters. Here, this is an interesting part. For classical layers, each layer is separated by an activation function. The problem that if we apply a ReLU activation function before the quantum, this means that half of the node will be 0 and half of will be 1. Half of node will be 0 and half of them will be non-zero. So this affects the encoding when applying angle embedding. So there is a clever workaround is to use a tanh from torch and map it from 0 to pi. So we are applying an activation function tanh, then also mapping it to 0 to pi so we can input it as an angle embedding. Okay. Building the hybrid. This is the weight shape, weight, number of layers, which is 2, number of qubits, and then 2. The hybrid model itself, it starts with the pre-processing. One layer, number of feature is 128. So the first layer is takes 128. Then into the second layer, which is takes 64. Then here we apply batch normalization to normalize the gradients and apply ReLU. So this is ReLU. So it's only two classical layers. Then we apply another layer with the rescaling. So we apply another layer here, 64. Then we apply the layer for scaling, 64, and the input is 4. qubits for and the layer for angle rescaling. So this all part is classical. Then for the quantum layer, there is quantum machining from torch layer. So it's very, very easy to integrate quantum layer into Torch framework. The same works for TensorFlow, but I like to use Torch. It takes the circuit itself, then weight shape from this. So after all of that, 4 will be fed into the quantum circuit. Okay, after the quantum circuit or quantum layer, we will add another last output layer, takes n qubit, which is 4, and then input it into 1. Uh, then we apply sigmoid because it's a binary classification problem. So the forwarding part is applying the pre-processing, the bottleneck layer, which do the angle rescale, then the quantum, then the post processing. So this is the model number of parameters for the classical pre-processing. It's 8,000 parameters, and for the quantum 16, and for the post classic it's only 5 parameters. Helper function, we only need get accuracy. If you remember from last session, we have several helper functions to take the expectation value, then map it into probability, uh, then use this probability for the loss, then from the to get the loss function, then from this observable probability we get the accuracy. So all of this part we are done by hand, but here we only need a get accuracy, which is a normal function for any classical machine learning model. We putting the model in eval mode, and um, here's a batch making a tensor for torch, then getting the props properties from the model, and then if it is um, more than half, it's 1, or less than half, it's 0, and then and do this condition with the labels. So it's a simple function for a binary classification problem. Okay, for the training, we initialize a normal Adam optimizer. Here, this is a dictionary, so we can assign two different learning rates for the this classical model with applying the classical, and for the quantum we're applying the learning rate focus. And for the loss function, in the previous session, we have implemented our own binary cross interval loss. Here we can use the binary cross interval loss from Torch framework directly, uh, making all our data in tensors, and then it's a normal uh, classical uh, it's a normal classical workflow. So if I give this part, this whole cell for a normal AI engineer, he won't suspect that there is a quantum layer in the model itself. So this is the beauty of this integration from Benelane and Torch framework. Okay, these are the result for 10 epochs. It for the training it reaches 100%, testing 94. It takes only 2 seconds because, of course, classical is very fast and it's a very, very small model. And for the quantum, Benelane uses the state vector directly, so it takes no time. Okay, these are the total parameters, um, confusion matrix, and these are the loss for training and testing, and the accuracy curve. Okay. So this is one approach for hybrid quantum neural network, is to first use the classical neural network to reduce the number of features. Taking Reducing the number of features makes you implement an easier and more efficient data encodings for the quantum circuit. So the classical here done the heavy lifting for the quantum models. Okay. Our second approach, which is here. Okay. It implements the quantum neural network first, then the classical neural network. Okay. So here, I was experimenting with other configurations, number of qubits, the number of classical hidden, how many the dimension I need after the quantum layer. Dropout, dropout is a normal configuration for a classical hidden layers. It reduces overfitting, because our problem is actually pretty easy for classical models. So for the training, it got a higher accuracy, and testing not that good. So reducing dropout balances this part, and the same two different learning rates. The same exact thing, loading the data, visualizing the data, normalizing MBCF. For the reduction here, I'm I'm reducing the data into the number of qubits, because here uh, the data or the quantum network is the first quantum. So it's the first part of the hybrid model. So the raw data will be inputted directly in the quantum model first. So I'm reducing the number of features into only 4 qubits. Okay, the same circuit, the same device, variational and torch, the same exact circuit, number of variational layer for the number of layers, and expectation value on each qubit. Visualizing the circuit, the exact same thing. Okay, for the build, we need first to understand or draw. The first one has classical layers, then the quantum one, then classical layers. Here, we are using the quantum neural network to reproduce a new representation of the features. So it takes 4 features and return also 4 new features, which are the observables. So, what is the advantage here? Let's say these 4 features are not in complex patterns and are not separated easily. So we train a quantum network to actually represent the data in a more separable way, so we can generate new features. Okay, so 4 features in, 4 features out. The 4 features are the expectation value on each qubit. So we initialize the quantum layer, the same thing, previous notebook, torch layer, the circuit and weight shapes. And for the classical, here we have patch norm as the same notebook. And then from the 4, we will make it into 32 feature a normal layer. So this is the quantum, which outputs 4, and another linear layer. This is a classical 4 to make it 32, and apply the dropout. Apply ReLU, then the dropout, then another layer from 32 into 1. So this is our output layer. Then we apply sigmoid for the binary classification problem. Okay. So it's a simple model starting with the quantum network, making a new features and input it into a normal classical machine learning model. So only 2 steps, the quantum part and the classical part. Okay. Here it's only 217 trainable parameters. The same helper function, accuracy. For the training, the same exact thing, optimizing using Adam optimizer, assigning different two learning rates, the same exact binary cross triple loss. And for the training, it's the same exact loop. Here it reaches 90% for training and 96% for testing. This is a confusion matrix and okay. So we need to understand what happens after the first quantum component. So if we run the circuit, and this is the expectation value density on each qubit. Uh, so the output for the first qubit, if you look closely, you can easily, by your eyes, separate between the two digits. I can just say, let's just say, for example, I have only the quantum layer, and I have the expectation value of qubit zero. Only the expectation value of qubit zero. I can just say, you know what? If it is more than zero point 0.2, then it's digit 6, and if it's less than zero point 0.2, it's digit 3. So the data becomes easily separable even with my eyes without the need of classical neural network in this case. So this is what quantum models are doing. It's representing the data in a different way. It can be easily used for uh, quantum or easily injected into the classical model. So this is the expectation value on each qubit. Loss curve and the accuracy. So to be fair, this is a uh, very simple example. Let's say I have 0 and 8. I believe it's a little bit hard. So let's test together. So it got 90%, pretty good, and the same thing. So this is a binary classification problem. Let's say you want to classify between all 10 digits. All you need to do is, of course, loading up, filtering the data, and you don't need to masking it. Use the whole 10 digits, and then balancing, of course, normalizing the same thing as the same quantum circuit. No changes here, no changes there. Building the hybrid. Okay. The difference will be here in the classical. You won't use a layer linear for 32 to 1. You will make it 32 to 10, the 10 classes, and then you want to apply sigpoint. You will apply softmax on the logits, the output from the previous layer, and then for the accuracy, you will apply softmax, then argmax, so you can sort the class. So the only different thing you do is all AI, or a classical AI. So the quantum part is modular. You can insert it in any model directly. This is the beauty of the hybrid models. So if you want to try it, you can try. You have the notebooks. You can try anything you want. So this is two approaches on how to implement hybrid models. Of course. So this is our session today, it's a small session, but I can add that our previous or all sessions uses state vector directly or an ideal simulator, which is good, which is okay for proof of concept, but in our real world, we need to actually have insight on the limitations, on the noise. So you can try noisy simulators. IBM provides fake backends, like here, fake Sherbrooke from Qiskit IBM runtime fake provider library. It is a fake backend, 127 qubits. It runs locally on your computer, but it applies, it's simulating the noise, the fidelity, the polarization, damping, and T1, T without errors, etc. So it's a good way to actually understand the effect of noise while training or testing your models. So it's the same thing. Binelian. Here we will add some libraries from Qiskit, the fake provider, and air simulator and noise models. The same configurations. We will add number of shots. In our previous notebooks, there was no number of shots because we are using the state vector directly. But here we must run the circuit so we can apply or simulate the noise. So we need to identify number of shots. Here it's a default value, 1024. You can increase it if you want a good approximation. Okay, so how we can use this fake backend from Qiskit into Binelane? So first thing, we need to initialize fake backend. Very simple. Then we get the noise model from backend and input the fake backend, which is fake Sherbrooke. Then we initialize the simulator with the noise model from the fake backend. So we now have the simulator with the noise configurations. Then when we define the device for Binelian, we will not use defaulted qubit. We will use something called Qiskit.air. So Binelian has also this good integration with Qiskit. You can just use Qiskit.air and initialize the number of qubits. Then the backend, which the noisy simulator that we have initialized here, and the total number of shots. So this this is it. No more um, no more modifications. Only changing the device, and all the notebook is exactly the same. So it's a modular approach, only changing the device that you are working on. It's the same exact notebook, copy paste, only changing the device. So it's Binrin and Qiskit have a very good integration between each others. Of course, it takes a lot of time, so I didn't actually run the notebook. Uh, but uh, but I can assure you it's working correctly. So, but it takes a lot of time. So this is a very good addition if you are working on a paper or a competition or a hackathon, to add some insights on the addition of noise on your training and testing of the models. So let's say you are a rich man and you have unlimited access on hardware from IBM, so you can integrate Binelane with IBM hardware. So you can train and test your model directly on IBM hardware. I can tell you it's very expensive. You need hours on QPUs to train your model, which is not feasible in our current era. But let's say you are one of these people. All you need is Qiskit runtime service from Qiskit IBM runtime. That's it. This library only. And the same libraries already implemented or already initialized in the lane. All you need is Qiskit IBM runtime. So the configurations are the same, adding the shots and uh, this part takes Qiskit server save account, takes your token and your instance. These two, when you are creating an account on IBM quantum computing platform or quantum platform, you can initialize an API. You insert your token here and the instance you have created here, so you can directly use the credentials. So you initialize service from the Qiskit runtime service. Then you choose which quantum computing you would like to run on. I like to use IBM Fizz right now. It's a balanced hardware. It won't takes much time from your 10 minutes or 10 free minutes. And this is the back end. And if you want to initialize the device for Benny Lane, all you need is to add an argument qiskit.remote. So on normal simulator, you will add qubit default.qubit, and for the simulator or noisy, you will add qiskit.air. But if you want to run on the cloud, on quantum computing, on a real hardware, you will input qiskit.remote. Of course, number of qubits, the backend itself that you have initialized, number of shots, and optimization level. Optimization level, it's a transpilation on how you want your circuit to be transpiled. There is from 0 to 3. Each optimization level will break down or decompose the gates even further, choose the qubits that will have the gates, but increasing the optimization level on quantum machine learning models, it is not the most efficient thing to do. You can start with one or even two. Don't use three, or start with three. Start with one. Of course, there are many other arguments if you want to do research or read the documentation on the internet. So this is the only part that you will have the modification. So the all cells and functions are exactly the same from the other notebooks. So the only difference is here that you initialized a different device which will access the your credentials and account on IBM. So let's say you are working on a paper. You will work first with um I don't will first work with, let's say, a hybrid model with a normal device, the default.qubit normal simulator that uses state vector directly. Then you can add shots, let's say shots. Okay. So first thing to do is to start with a state vector directly. Then try, let's say, 100 experiments. Try as you want. You are working with a state vector directly, so it takes seconds for training. So let's say you have grouped some configurations, a certain number of qubits, certain number of layers, encoding types. You have tried different experiments, so you can add the shots. It is still still is a simulator, but with running the circuit. So you can have a taste on the time it would take to actually run the circuit on the simulator. So after the ideal simulator, you can the same model. You have narrow it down to only few configurations. you can try on noisy, adding some noise. Raise the noise. So with this few, like you are making a table with these few configurations, you start adding noise. It will take 5 to 10 more times running more than the ideal simulator. So be ready. So it will take much more time. Then let's say you have completed the state vector and ideal and noisy, and then you are have access or have some fund. You can run on a hardware, so you can try, or you want to proof of concept. You can only, let's say, running on hardware with only one data point, or only, let's say, one epoch, so you can proof of concept on that actually the model can be trained on hardware if it is applicable. So you can use running your model on hardware. So this is the workflow I recommend working on a research paper or um, a hackathon or a competition. Most research papers actually stop here or noisy, or even they don't go into using the noise simulator for applications. So it would be a great addition, either adding the noise and the hardware. Okay, so are there any questions about the session so far? Uh, ca- can you hear me? Yeah. Okay, so we conclude, before we conclude the track, this is the task or the final project for the track. You will have 2 weeks to complete this task or a project. It's a very, very good project. If you have actually done it and really truly understand it, you can add it into your CV, add it on LinkedIn. It would be a very, very great addition. The project is about investigating an advanced topic in quantum machine learning. The goal is not only to understand the algorithm, but to critically evaluate its implementation, potential advantage over classical methods. So let's say you are a reviewer and you are working on a paper. This is what you are dealing with, to actually evaluate if it has advantage and the implementation and the comparing it with different or other classical methods. So each student or group up to three, you can, let's say, group on the WhatsApp group. You can make a team up to 3 members, or you can do it alone if you want. We'll select one topic and do uh, some analysis. So the topics are quantum autoencoders, quantum BCA, quantum key means. These two are actually unsupervised learning techniques, so it's great if you choose these two: quantum BCA and quantum key means, quantum anomaly detection, and quantum reservoir computing. So your team or you will choose one of these topics to do the analysis. So what the report should have: explain how a quantum machine model works at a system level, identifies the role of quantum versus classical components, analysis whether the model provides any realistic advantage, connect the model to known classical machine learning techniques, demonstrate basic implementation or logarithmic understanding. So the required structure: problem definition, the algorithm explanation, hybrid architecture, step-by-step pipeline, and implementation. You can use Benelane, Cascade, or even if you don't want to write an implementation, you can write a detailed pseudocode explaining the full workflow. So as a bonus, if you actually run the implementation using a small data set, okay, and classical comparison and limitation challenges, uh, and lastly, critical evaluation. Okay, the submission is a PDF report, 6 to 10 pages, include figures if you actually run the model, diagrams, circuit illustrations where appropriate, and code if implemented. Timeline 2 weeks from now. Late submission may not be accepted unless prior approval is given. The criteria: understanding and clarity, hybrid analysis, critical thinking and evaluation, implementation, or pseudocode. Okay, so I need you to focus on understanding analysis. Use diagram to explain complex ideas. You are encouraged to consult research papers, but explanation must in your own terms. So good luck with this project. If you are actually done this project, it's a very, very good milestone in your academic and work career. So any questions about this task?
It's a good challenge. It's a good
Yeah,
challenge.
yeah,
Yeah.
yeah, I know.
It's
Yeah,
necessary think, more think.
yeah. It would be great if done correctly on the CV or LinkedIn or GitHub. So it's a great project. Okay, so in the classroom there are 20 active students, or let's say it's not 20 active, 15 active students, or maybe yeah, 15 to 20 active students. So if you want, you can group yourself as teams. You can ask on WhatsApp group, uh, and when submitting the project, if you are a group, just list your names on the PDF report. Okay, so the deadline is 2 weeks from now. I will share the task um, after the session directly. So the participants that couldn't attend today could see and choose their teams, or if you want to work alone, that's okay also. No problem. I have a midterm exam from 23 to 44. So okay. So it's a great point. Of course, midterm. So let's say 2 weeks from now. Yeah. So let's say if you give it 1 hour daily, if you're working with other members, you are not required to give an implementation on actual run the model itself. You can uh, you can work 3 4 days with problem definition. You can use a simple topic. Let's say quantum BCA is the simplest of them all. You can work on the problem definition, the explanation, how the pipeline works, and the comparison and limitations. So it won't take much. I'm sorry for your exams. Yeah, it's tough, I know. So yeah. So if you need any other help, we can in the group we can help you. So I believe you can also team up with other members that are interested. Okay, great. Okay, so any other questions about the session or even the whole track in general? Okay, guys. Thank you for attending and the consistency and the commitment um, for the track. See you in other future tracks. Okay, thank you.
Thank for all. Excellent course.